Hi, this is Schwartz from MasterMathMentor.com. This is video BC17. The topic is infinite series, and it covers the BC manual, pages 92 through 94. If we are given a sequence, A sub n, then we will define S sub n as the sum of the first n terms of the sequence. Mathematically, we say S sub n is equal to sigma I equals 1 to n of a sub I, meaning it is a sub 1 plus a sub 2 plus a sub 3 plus plus a sub n. We will call this sum of a sequence a series. We now define S to be sigma I equals 1 to infinity of a sub I, which is a sub 1 plus a sub 2 plus a sub 3 plus plus a sub n plus . This is called an infinite series. It represents the sum of all the terms of the sequence. So if we have sigma n equals 1 to infinity of 3n, that would be defined as 3 plus 6 plus 9 plus plus 3n plus . The nth term, which would be 3n, is called the general term of the infinite series. The major question for the remainder of this video and all the videos following is, does the infinite series A sub n converge or diverge? A sequence converges if its nth term approaches a limit, meaning the limit of A sub n as n approaches infinity is equal to L. But an infinite series converges if the sum of its infinite terms approaches a limit, meaning the limit of S sub n as n approaches infinity is equal to some number L. Divergent infinite series are usually easy to spot. When you write out the terms, it becomes quite clear that it is divergent. For problems 1 through 3, explain why these infinite series are divergent. 1. The summation n equals 1 to infinity of 2 to the n is 2 plus 4 plus 8 plus 16 plus . And it is obvious that these terms get bigger without bound, and therefore the sum will get bigger without bound. In number 2, n equals 1 to infinity of the square root of n is 1 plus the square root of 2 plus the square root of 3 plus 2 plus . Again, these terms are getting bigger without bound, and therefore their sum gets bigger without bound. 3 reads summation n equals 0 to infinity of cosine n pi. And this will be cosine 0 pi plus cosine 2 pi, etc. And it becomes 1 minus 1 plus 1 minus 1 plus . Many students think that this is 0. But if it is 0, then if we use parentheses around the terms, we get 1 plus quantity negative 1 plus 1 plus negative 1 plus 1 plus ... which would give us 1 plus 0, which would be equal to 1. And therefore, 1 is equal to 0, and that's impossible. So this is also a divergent series. Convergent series are far more difficult to prove convergent and even more difficult to find their sums. Here are 2 examples of convergent series where we can actually find the sum. Number 4 reads the summation n equals 1 to infinity of 1 over 2 to the n. The best way of looking at this is to write out the series. And that will be 1/2 plus 1/4 plus 1/8 plus 1/16, etc. S1 is the sum of the first term, which is simply 1/2. S2 is the sum of the first two terms, which is 1/2 plus 1/4 or 3/4. S3 is the sum of the first three terms, or 7/8. S4 is the sum of the first four terms, which is 15/16. It should be apparent that in each of these, the numerator is one less than the denominator. So the sum of the first n terms is 2 to the n minus 1 over 2 to the n. And if we look at the limit of s sub n as n approaches infinity, that is equal to 1. So the sum of the terms 1 over 2 to the n, where n runs from 1 to infinity, is 1. Number 5 reads 0.9 plus 0.09 plus 0.009 plus 0.0009 plus ... We can write a rule for this series, summation n equals 1 to infinity of 9 over 10 to the n. S sub 1 is 0.9, S sub 2 is 0.99, S sub 3 is 0.999, S sub 4 is equal to 0.9999. So S will be 0.9 with the 9's continuing forever. And therefore the limit as n approaches infinity of S is equal to 1. Now students don't like this. They will argue that 0.9999 with the 9's going on forever is not 1, it's just short of 1. However, there are many proofs to show that 0.999 going on forever is 1. The easiest one is to say that 0.3333 with the 3's going on forever is 1/3. Students will not dispute that. If we multiply both sides of that equation by 3, we get 0.9999 with the 9's going on forever is equal to 3 times 1/3, which is 1. Strange things happen when we play around with infinity. Finally, there are several rules that work with convergent series. If we have two convergent series, summation n equals 1 to infinity of a sub n, and we'll say that that sum is a, and summation n equals 1 to infinity of b sub n, and we'll say that the sum is b, with c a real number. Then we can say that the summation n equals 1 to infinity of c a sub n is ca. We can take the c and take it outside the sigma sign. The summation n equals 1 to infinity of a sub n plus b sub n is simply a plus b, and the summation n equals 1 to infinity of a sub n minus b sub n is a minus b. We now define a convergence test. A convergence test is a procedure to determine whether an infinite series will converge or not. When we apply a convergence test, there are three possible results. Either the series converges, the series diverges, or the test is inconclusive. Convergence tests do not tell you what a convergence series converges to. It just determines whether it does or not. Our first convergence test is really a divergence test. It is called the nth term test, and it is probably the most important test in our arsenal. It should be applied before any other test. The nth term divergence test says that if a sequence a sub n diverges, then the infinite series, summation n equals 1 to infinity of a sub n, will also diverge. If the sequence a sub n converges to 0, then the infinite series, summation n equals 1 to infinity of a sub n, could converge. And if the infinite series summation n equals 1 to infinity of a sub n converges, then the sequence a sub n must converge to 0. Let's see an example. Suppose the sequence a sub n equals n over 2n plus 1. This generates the sequence 1/3, 2/5, 3/7, 4/9, etc. And we can see the points in a graph. Now let's consider the series, summation n equals 1 to infinity of n over 2n plus 1. This is 1/3 plus 2/5 plus 3/7 plus 4/9 plus dot dot dot. And we would like to determine whether this is convergent or divergent. We see the points in the graph of the partial sums. The first sum is 1/3. The second sum is 1/3 plus 2/5. The third dot would be 1/3 plus 2/5 plus 3/7, etc. It must be emphasized that our nth term test will not determine whether any series, and including this one, will be convergent. It will rule out convergency, but not ever prove it. As n gets large, we are adding numbers that are essentially 1/2. For instance, when n is equal to 100, we are adding 100 over 201. When n is 1,000, we are adding 1,000 over 2001. And these numbers are getting closer and closer and closer to 1/2. Which means that we are essentially adding 1/2 plus 1/2 plus 1/2 and continually doing that forever. So our conclusion is, because the limit as n approaches infinity of n over 2n plus 1 is equal to 1/2, and that is not 0, then the series summation n equals 1 to infinity of n over 2n plus 1 diverges by the nth term test. Summing up, the nth term test examines the infinite series summation n equals 1 to infinity of a sub n. That series must diverge if the limit as n approaches infinity of a sub n is not equal to 0. It can converge if the limit of a sub n as n approaches infinity is equal to 0. And if we know that the series summation n equals 1 to infinity of a sub n converges, then the limit as n approaches infinity of a sub n has to equal 0. In problem 6, we are given 3 infinite series and asked to apply the nth term test to each of them. 6a reads the summation n equals 0 to infinity of 4 to the n power. It is always a good idea to write out the first few terms of a series to get a sense of how it is behaving. This series is 1 plus 4 plus 16 plus 64 plus dot dot dot. And our nth term test says that this is clearly divergent because the limit as n approaches infinity of 4 to the n is equal to infinity. 6b reads summation n equals 1 to infinity of 1 over n. Our series is 1 plus 1/2 plus 1/3 plus 1/4, etc. Our nth term test says that this could converge as the limit as n approaches infinity of 1 over n is equal to 0. Do not trust your instincts with problems like this. A typical reaction is we are adding smaller and smaller and smaller numbers, and therefore this series must converge. In fact, it doesn't, as we will see in the next video. 6c reads summation n equals 1 to infinity of 3n over n factorial. Our first few terms are 3 plus 6 over 2 plus 9 over 6 plus 12 over 24 plus 15 over 120, etc. At first, our numerator is greater than our denominator, but very quickly our denominator becomes greater, in fact much greater. And we find that this could converge as the limit as n approaches infinity of 3n over n factorial is equal to 0. This is the convergence test procedure. We want to test whether the series summation n equals 1 to infinity of a sub n is convergent or divergent. The first thing we do with it is we apply our nth term test. If the limit of a sub n is not equal to 0 as n approaches infinity, we know that the series is divergent and we can stop. However, if the limit of a sub n as n approaches infinity does equal 0, that means that it could converge, and we have more work to do. We will determine its form, and we will see over the next few videos there are many different forms for these series. We will have a test for each one of the forms, and each one of the tests will tell us whether it is convergent or divergent. So if it is in the form of number 1, we will apply the number 1 test and determine that the series is convergent or divergent. Our first special form of an infinite series is called a telescoping series. With a telescoping series, if it converges, you will also know the number to which it converges. Our first example is summation n equals 1 to infinity of 1 over n minus 1 over n plus 2. We first apply our nth term test. Limit as n approaches infinity of 1 over n minus 1 over n plus 2 is 0 minus 0, which is 0, so the series could converge. Next, we will write out a series of terms. We will look at the summation n equals 1 to m of 1 over n minus 1 over n plus 2. And we get 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6 plus 1/5 minus 1/7 plus dot 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 plus 1 over m minus 1 over m plus 2. And notice that everything will cancel. That's why it's called telescoping. And except the 1 and 1/2. And the last terms, 1 over m plus 1 minus 1 over m plus 2. We now take the limit as m approaches infinity of 1 plus 1/2 minus 1 over m plus 1 minus 1 over m plus 2, and we get 1.5. So the sum of this infinite series is 1.5 because all terms will cancel except the 1 and the 1/2. In general, a telescoping series can have a finite number of terms that do not cancel, but eventually there will be a positive term that will be canceled out by a negative term, and this process happens forever. If the limit of the nth term approaches 0 as n approaches infinity, then the series converges. Sometimes a telescoping series occurs, but in disguise. If we look at the summation n equals 1 to infinity of 4 over 4n squared minus 1, writing out the terms, we get 4 over 3 plus 4 over 15 plus 4 over 35 plus 4 over 63 plus dot dot dot. There are no pluses and minuses here, so there is no way that you would get cancellation, this does not appear to be a telescoping series. Still, the limit as n approaches infinity of 4 over 4n squared minus 1 equals 0, so the series could converge. But we now use our partial fractions Heaviside method and realize that 4 over 4n squared minus 1 can be written as 2 over 2n minus 1 minus 2 over 2n plus 1. And therefore, we can now look at the summation n equals 1 to infinity of 2 over 2n minus 1 minus 2 over 2n plus 1. This gives 2 minus 2/3 plus 2/3 minus 2/5 plus 2/5 minus 2/7 dot dot dot. And it should be apparent that all the terms will cancel except the first and last term, and therefore we have the limit as n approaches infinity of 2 minus 2 over 2n plus 1, and therefore that is equal to 2. So the sum of these fractions is exactly 2. The figure shown is a square of side 8 inches, and the midpoints of the square are vertices of an inscribed square with the pattern continuing forever. We have two questions. If we add up the perimeters, are they convergent? And if we add up the areas, are they convergent? These questions will be answered in the next video. Stay tuned.